The Kenyan teacher here one more time. In this video, we have the pleasure to present expected responses to questions that were derived from Form 4 work in Chemistry Paper 1 for the year 2022. According to our analysis, Form 4 work contributed a total of 30 marks in this paper, which translates to 37.5% of the total score. We ask that you be with us until the end of this video. We begin with question number 3. 3 part A. We are asked to write a thermochemical equation for the formation of carbon 2 oxide. This is what we call enthalpy of formation. So our product carbon 2 oxide must be formed from its constituent elements, which in this case is carbon in solid state and oxygen in gaseous state. Now, when it comes to balancing, ordinarily we would balance this equation with a 2 on carbon and a 2 on carbon 2 oxide. But by definition, and for enthalpy of formation to hold, we need to maintain 1 mole of carbon 2 oxide at this point. So balancing with a 2 on carbon and a 2 on carbon 2 oxide would go against the definition of enthalpy of formation. For that matter, to balance, we would be forced to use a half on oxygen. That is good enough for the 1 mark, but for a candidate who has read far and wide, you know that a thermochemical equation needs to show the enthalpy change of formation on the far right of the equation. And because this question didn't give us the value, a candidate would go ahead and quantify this heat to be X kilojoules per mole. So this would be the complete thermochemical equation for the formation of carbon 2 oxide. But if a student ended at just balancing this equation with a half on oxygen without including the delta HF here, we would still give that 1 mark. To part B, we have energy level diagram here as figure 1, and we are told to use it to answer the questions that follow. So on the x-axis we have energy, and we have at energy level 0 we have carbon in solid reacting with oxygen in gas. Then down here, if we use the given scale, we realize that 1 small square here represents 10 kilojoules, because from 0 to negative 200 there are 20 small squares. So that would mean 1 small square represents 10 kilojoules. So going down up to where we have the thick line, you realize that we have 11 small squares. For that matter, the amount of energy at this level is negative 110 kilojoules, where now we have carbon 2 oxide in gaseous form together with oxygen being placed there. Then going down further, we have up to negative 400 kilojoules, where now we have carbon 4 oxide. Now, the energy difference between what we have here and here would be 290 kilojoules, because we are moving from negative 110 to negative 400. The difference down here is negative 290 kilojoules of energy. So with that analysis, we can now go ahead and answer the questions that were brought from the graph or from the energy level diagram. Part A, we are told to determine the enthalpy change of formation of carbon 2 oxide. So here we need to go back to our graph, and we see that for us to form carbon 2 oxide from carbon and oxygen, we need negative 110 kilojoules of energy. So that becomes our answer to Roman 1 of part A. So here we have negative 110 kilojoules, of course, per mole of carbon 2 oxide formed. The question goes ahead now to ask us about the combustion, the enthalpy change for combustion of carbon 2. So when you burn carbon 2 oxide in air, you get carbon 4 oxide. And as we have already realized, this amount of energy should be negative 400, and from it we subtract negative 110. If you do this, we are able to get negative 290 kilojoules again per mole for combustion of carbon 2 oxide. We proceed to question number 5, part B, which also came from Form 4 work. The topic now being organic chemistry 2. In question number 5, part B, we are told to draw the structure of an alkanoic acid. Alkanoic acids belong to homologous series with a general formula of RCOOH. Then, a candidate was then asked to draw the alkanoic acid whose formula has 5 carbons, 10 hydrogens, and 2 oxygens. So this one would be quite easy. A candidate would draw the 5 carbons in a straight chain. Then the last carbon would have the double OH. And because we are told to draw the structure, we need to open up every bond. Now, the rest of the carbons would then have hydrogens. This would be the required structure for our pentanoic acid. That is C5H10O2 for 1 mark. Next question is number 6. Number 6 was borrowed from reaction rates and reversible reactions. Number 6, the following equilibrium exists in a closed system. So we have, this is dinitrogen tetraoxide, which is yellow, on the left, and we have nitrogen oxide, which is brown, on the right. Of course, the delta H given here, as we always say, is for the forward reaction, is positive 27.5 kilojoules. So it means that the enthalpy change for the backward reaction would now be negative 27.5 kilojoules, meaning that the forward reaction is endothermic while the backward reaction is exothermic. From that analysis, the question is now telling us to state and explain 2 conditions under which the intensity of the brown color of the equilibrium can be increased. So, for us to increase the intensity of the brown color, we need to favor, or we need to shift our equilibrium to the right. And remember, we have said that the forward reaction is endothermic. It needs heat. So one of the conditions that we can apply to shift our equilibrium to the right is to increase the temperature. So, increase in temperature would increase the intensity of the brown color. So we need to go ahead and explain that formation of brown NO2 is an endothermic process. Is an endothermic process that is favored by increase. Is favored by increase in temperature. So, for mentioning the factor that would increase the intensity of the brown color, half a mark, and the explanation, 1 whole mark. Next thing that we would do to increase the intensity of the brown color would be pressure. So if we look at the equation, we have 1 volume of gas on the left and 2 volumes on the right. So if we would want the equilibrium to shift to the right, remember this is the side with more gas molecules, then what we would do is to decrease the pressure. By decreasing the pressure, the equilibrium would shift to the side with more gas molecules, which in this case is the right hand side. And that is where we have brown nitrogen 4 oxide. So after identifying the factor for half a mark, we'd go ahead and explain that production of brown nitrogen 4 oxide is favored by low pressure for 1 mark, totaling 3 marks for question number 6. Next question from Form 4 was question number 7. Question number 7 tested electrochemistry, specifically on oxidation numbers and a bit of organic chemistry too. So, part A, determine the oxidation numbers of hydrogen in this formula. So here we know the oxidation state of calcium would be positive 2. If we add this to 2, the oxidation number of hydrogen, we should get a 0. So when you work out this, we get 2H is -2 if we subtract -2 on both sides, and the oxidation number of hydrogen becomes -2 divided by 2, which is -1. So for this case, a student was only expected to know the oxidation number of calcium, which is +2. So a half a mark for the relation there and a half a mark for the answer. How about oxygen in OF2? So here, oxidation number of oxygen, if you add 2 twice oxidation number of fluorine, which is known to be -1, we should get a 0. This of course is oxygen. Now, by working out, we get oxidation number of oxygen to be +2. That is, when we work this out, we get -2, and then for us to eliminate it on the left, we would add 2 both sides. That gives +2 as the oxidation number of oxygen. Half for that relation, half for the answer. Part B, we are told to write an ionic equation for the reaction between sodium hydrogen carbonate and ethanoic acid. The formula of ethanoic acid is learnt in Form 4 under organic chemistry 2. So, when we are doing ionic equations, we are supposed to write the usual balanced chemical equation. So we have sodium hydrogen carbonate in aqueous state. Ethanoic acid has the formula CH3COOH. This is what a Form 4 needs to know. Because of the 2 carbons, it is called ethanoic acid. It would come in aqueous state After this reaction, we expect to form sodium ethanoate, CH3COONA. Again in aqueous. Allow me to break my equation because it's very long. We shall get carbon dioxide as well, and we shall get water. Of course, it balances out like that because the mole ratio is 1:1. After these, for us to get the ionic equation, we would need to break the aqueous solutions into the ions that are present. So beginning with sodium hydrogen carbonate, we have sodium ions in solution and hydrogen carbonate ions. Of course, negative, sorry, they are anions. In the ethanoic acid, we have the ethanoate ions and we have hydrogen ions. On the right hand side, we would break sodium ethanoate into the ethanoate ion and sodium ions. And of course, carbon dioxide gas does not have ions, same to water, which remains as gas and liquid respectively. From here, we are supposed to identify our spectator ions, which we cancel out. Spectator ions would appear on both sides of the equation. So sodium is here and is there. We cancel that out. Ethanoate is here and there. We cancel that out. So to get now the ionic equation, we need to rewrite this hydrogen carbonate ions reacting with hydrogen ions, and we are able to get carbon dioxide gas and water. This is the sure way of obtaining an ionic equation, and this discussion we normally hold in Form 2. So write the normal balanced chemical equation as written here. Break your aqueous substances into the ions, identify spectator ions, cancel them out, then rewrite the equation excluding spectator ions. What you obtain will be called an ionic equation. We proceed to question number 11, borrowed from acids, bases, and salts of Form 4, more specifically on water hardness. In an experiment to test for hardness of water from different boreholes, soap solution was added to a liter of the water, and volume of soap solution required to lather to start forming was recorded. Table 2 shows the results. So we have water sample 1. Before boiling 25, after boiling only 3 cubic centimeters of soap was used. So a candidate who understands water hardness knows what is going on here. By mere boiling, we are able to actually make sample 1 soft because we are able to use very little soap after boiling. So here we have what we call temporary hardness, which is removed by mere boiling. To sample 2, we used 12 before boiling, that's volume of soap. It reduced slightly to 8. For sample 3, the volume of soap didn't change after boiling. Sample 4 the same, but at least we are using very little soap in sample 4. Sample 5, there was a slight change from 25 cubic centimeter to 24. So we are asked to select water samples that show temporary hardness. Here, a candidate would go for sample 1. We've seen the big difference. We would also accept sample 2. Of course, the amount of soap used was able to decrease a bit after boiling, and even sample 5, where we had a slight difference. So if you're able to use less soap after boiling, that sample qualifies to be temporarily soft, temporarily hard. So any of those three have a mark. No hardness at all. This one we are able to see only in sample 4 because we are using very little soap to form lather. Then for Aeroman 3, we are asked to identify samples that show both temporary and permanent. Here, we would go for sample 2. Even after boiling, we were still able to use so much soap, which means we removed the temporary hardness through boiling, but some hardness, which was permanent, still remained. So we have sample 2, and the same case was seen in sample 5, where by boiling, we reduced the amount of soap needed by just 1 cubic centimeter. So again, any of those two would earn ourselves half mark. We proceed to part B of question number 11. So in part B, we are asked to describe how water hardness can be removed using an ion exchange resin. So here, the description would be that hard water is run down a column. Hard water is run down a column that contains the ion exchange resin. This is running down half mark. We continue that the calcium ions and the magnesium ions, which are actually responsible for water hardness, are exchanged for sodium ions, which are not responsible for hardness of water. Once that has been done, we say that soft water comes out of the column. So that is the description of how water is softened using ion exchange resin. So a half a mark for running down, a half a mark for mentioning the ions responsible for water hardness, and a half a mark for the ion that is normally exchanged for those responsible for hardness. We proceed to question number 12. Question 12 tested us on the understanding of electrochemistry 2, discussed in Form 4. So, products of electrolysis at the electrolytes for aqueous solutions depend on 3 factors. So the examiner gave us 2 of those factors, that is concentration of the electrolyte and nature of electrode. The third factor that affects preferential discharge, as we know, is position of ion in what we call the electrochemical series. This is what the examiner expected by telling us to state another factor that affects the products of electrolysis. So for part B, we are told to complete table 3 to show products of electrolysis of dilute calcium chloride and concentrated calcium chloride at the anode and cathode. So what we know is that dilute calcium chloride contains calcium ions in low concentration. They contain chloride ions again in low concentration, but we have hydroxyl ions, very high concentration because there's so much water, and hydrogen ions again in high concentration. When it comes to now the concentrated salt, calcium ions are highly concentrated, same to chloride, but the concentration of hydroxyl ions are very low, same to hydrogen ions. So, products of electrolysis at anode, beginning with dilute, we shall discharge hydroxyl ions. When you discharge hydroxyl ions, you obtain oxygen gas. So that would be the product at anode. For the cathode, we shall discharge hydrogen ions to give us hydrogen gas. When it comes to concentrated calcium chloride, at anode, now concentration is going to affect our discharge. So instead of hydroxyl to give us oxygen, we shall now discharge chloride ions to produce chlorine gas. For the cathode, concentration doesn't affect discharge, so we shall still discharge hydrogen ions to give us hydrogen gas, each for a half a mark, giving a total of 2 marks. We proceed to question 14, testing on organic chemistry 2, particularly on polymers. Give an example of a natural polymer. It has to be natural, made of cellulose material. Here we have quite a number of natural fibers made of cellulose. We have cotton, there is sisal, there is wood, we have paper, and even wool would give a candidate that half mark. For the natural polymer made of a hydrocarbon, we'd go for rubber, which we can also call latex, for the next half mark. B, we are told that part of the structure of perspex is shown here. So for this one, we have 3 repeat units. Up to here is a repeat unit, and up to here is another one. So we are now told to draw the structure of the monomer. Very easy. A candidate was expected to just identify the repeat unit. So you pick that repeat unit and you introduce a double bond in between the carbon atoms for us to get the monomer. So it is as easy as what I have just done for 1 mark. Identify the repeat unit, pick it up, introduce a double bond between the carbon atoms in the repeat unit. Give 2 properties of perspex that make it suitable for use in making lenses. The most important is that it is transparent. We can also say that it is strong. Somebody can argue that it is hard. Somebody can even talk about free of charges. And we also have another property that it has consistent refractive index. And now to number 16, testing on radioactivity. Number 16, part A. The graph in figure 2 shows radioactive decay curve of a radioactive isotope. So we have mass on the x-axis as indicated there, and time in hours on the y-axis. Of course, this tangent that is shown here was not part of the graph. I have drawn it to help us do a question that was asked about the same. So the first part, we are asked to use the graph to determine the half-life of the radioactive isotope. Here, a candidate was supposed to pick 2 masses. The masses range from 0 here to 6, actually 7 up here, but 7 is not covered by the curve, so we would pick between 0 and 6. What we need to do is to identify 2 masses, with one being half the other. So for purposes of illustration, I will pick 3, mass 3 grams, and I check how long it needs to disintegrate. So if I use the graph, I realize that 3 grams of my isotope needs 100 hours. This would be my time 2. Then double that to 6, so that 3 and 6 become masses. where one is half the other. So when I do the same for gram 6, I'm able to get a mass here. You are supposed to use a ruler, but let me just use free hand. This mass is giving me time of just 10 hours, because you realize the scale used on the x-axis is 1 small square for 10 hours. So this becomes 10 hours, which is now my T1. Now, to get half-life, you simply need to get the difference between those two timings. Again, a candidate can use another set. You don't need to necessarily go for 3 and 6. Somebody can pick 2 and 4, and somebody can also pick 1 and 2. That would also work. So for our case, we would argue that my time 2 was 100 hours. Time 1 is 10 hours. So then our half-life, that is T half, would be given by T2 minus T1. This is 100 minus 10, and I'm able to get 90 hours for 1 Mach. For part 2, the examiner is asking me to find the rate of decay at 150 hours. So for that matter, this is instantaneous change, as we always say in maths. So a candidate is supposed to simply draw a tangent at time 150. This is where we have time 150, 100, 200, so in the middle here will be 150. You draw a tangent at that point, and then you find the gradient. So if I did this, I would have 2 points here. This point here, using our scale, is 240, 0.5. And this other point here is 60, 3.3. A candidate can use different sets of coordinates for the same. So here, the rate would be given by change in y over change in x. If I use my coordinates, change in y is 3.3 minus 0.5. And change in x is 60 minus 240. That gives me 2.8 if I do the subtraction over negative 180. If I do this math, I get a rate of change of negative 0.01555. Of course, these are grams per hour as my rate. So this is the calculation that we transfer to our space, and we've been able to get rate of 0, of course negative 0.0155 grams per hour. So candidate, don't forget, when you are asked an instantaneous rate of change, you have to draw the tangent to the curve at the point in question. For part B, the half-life of 2 radioactive isotopes A and B are 8 days and 5.2 years respectively. We are being told that given that both of them emit beta radiation, why would A be more suitable in treatment of a disease? Of course, this is treating a human being, and for that matter, A would be the most suitable. So A has a shorter half-life than B. Of course, that is true, 8 days and 5.2 years. So, because of that, this A will clear. It will clear from the body. It will clear from the body of that human being we are treating faster. Thus, not exposing the patient. Thus, not exposing the patient to radiation. for a long time. You can imagine if we were to put this patient to radioisotope B for 5.2 years, this would be within the cells, and that is when now we find even the healthy cells being affected. So it's 1 mark, A having shorter half-life than B, first half mark, and not exposing the patient to radiation for a long time, the next half mark. With that, we proceed to number 23, borrowed from the topic metals, in particular metal iron, again discussed in Form 4. Part A. Iron is extracted from hematite ore. If the ore contains oxide of silicon and aluminum, explain how these impurities are removed. So these impurities react with calcium oxide. Of course, this is one of the things that we put in together with the ore. So they react with calcium oxide to form, I'll write this in symbols to save on space. This is calcium silicate and calcium aluminate. They have that formula. Now, once we form calcium silicate and calcium aluminate, we then remove them as slag. So 2 marks, calcium oxide 1 whole mark, half for calcium silicate, a half for calcium aluminate. Part B, the extraction process of iron produces waste gases. We are told to state how these waste gases can be used to lower the operational costs. What we do is that the waste gases, of course, are of high temperature. That is true. The waste gases are of high temperatures. So this heat here, the heat that makes them to be very hot, can be recycled. To do what? To preheat the incoming air or the incoming gases. So that way we are able to reduce the operational cost. So the heat or the high temperature of the waste gases, half mark, preheating another half mark, or recycling for that matter. We move to question number 24. 24 tested on reversible reactions and rates. So we are asked that, or we are told that when chlorine is bubbled into a sample of water, the solution smells strongly of chlorine. If aqueous sodium hydroxide is added to the solution, the smell disappears. So the equation is down here. Of course, chlorine and water reversibly reacting to produce HCl and HOCl. So we are told that with reference to the equation for the reaction, an equation has been given that chlorine of course reacting with water reversibly. Chlorine reacting with water reversibly to form HCl and hypochlorous acid. So why is the solution smelling strongly? This answer would be very simple. We would simply tell the examiner that chlorine reacts partially. It reacts partially with water. Now, because it reacts partially with water, the strong smell is then due to presence of chlorine molecules. Since equilibrium tends to lie on the left. It was just 1 mark, So a half for partially reacting with water, that is chlorine, and presence of chlorine molecules for the next half mark. How about addition of sodium hydroxide removing the smell? So we know sodium hydroxide is an alkali that would react with these two acids. So then we shall shift the equilibrium to the right in order to raise the concentration of the two. So our candidate was expected to tell us that sodium hydroxide neutralizes both HCl and HOCl. Once we do this, equilibrium then shifts to the right. Equilibrium would then shift to the right and once this has been done, when equilibrium are shifted to the right, then chlorine molecules are consumed. Hence, the smell disappears. So we are shifting the equilibrium to the right in an attempt to raise the concentration of these two acids which we are neutralizing. So 2 marks, sodium hydroxide neutralizing HCl and HOCl, 1 mark, equilibrium shifting to the right, another mark. We finally examine question number 26, which came from acids, bases, and salts. Again, a topic taught at Form 4. So we are given the formula of a complex ion formed when zinc sulfate reacts with aqueous sodium hydroxide. This is actually zinc tetrahydroxo. So the charge is X there. So we are told to explain how the value of X is determined. So here, we would start with oxidation number of zinc, which we know is positive 2. Then the OH minus you see here, we normally has a charge of negative 1. Of course, we know that. So to get X, we will add the oxidation number of zinc, which is plus 2, to 4 times the hydroxyl ions. 4 times hydroxyl ions, and each one of them has a charge of negative 1. So from here we get X as positive 2 minus 4, and that gives us a charge of negative 2 to be the overall charge for our tetrahydroxo zinc ion. A half for getting the ON of zinc, a half for the charge of OH, a half for that relation, and a half for the final charge or the value of X. With that, we've come to the end of our video where we have reviewed Form 4 syllabus as tested in the year 2022 KCSE Chemistry Paper 1. Thanks for being with us, and continue keeping it right here for more KCSE reviews.